Hey everyone. So welcome to the weekly G number 3, and today I'm going to talk to you guys about a system that I think is very interesting. It's a system that has a negative heat capacity. But before I begin, first I want to give a shout out to Stanford football for beating USC last night. Totally kick-ass. Stephon Taylor actually was a freshman in Gavilan while I was the resident tutor in Lauro, so I feel a bit of a personal connection here. Of course, I talked to him all of maybe once or twice, so not that personal, but still feeling the Stanford pride. Anyway, getting back to heat capacity. So I should first talk about what heat capacity is. So heat capacity is, I'm going to give it the symbol C, and C is equal to the derivative of energy with respect to temperature. And usually the way that people are introduced to heat capacity is through the idea of specific heat. Specific heat. And in specific heat, usually the way people are introduced to this is in high school chemistry, where they say something like delta H is equal to mc delta T, which is one of those equations that has been burned into my memory forever. And the C that they're referring to is actually specific heat, which is the same thing as heat capacity, except that you divide by the mass. So this kind of whole thing together is what I call the heat capacity. So that's supposed to be a big C as opposed to be a little c. And if you remember, there are times when you saw specific heat, it was basically when you were doing something like heating water, and you wanted to see how many calories of energy you had to add to the water in order to heat it up by a certain number of degrees Celsius. So you do something the C was usually something like 1 calorie per gram degree Celsius. Delta T was something like 20 degrees Celsius. So, and then the question was to figure out how much energy you had to add to the water in order to heat it up that much. So that's what heat capacity is. And of course, you expect that this heat capacity is going to be positive. The reason is that if you're adding energy into the system, the temperature is going to go up. Or you can think of it the other way. If you're heating a system up by increasing the temperature, it's going to make the particles inside of your system move faster, which means that their energy is going to be higher. And so that's kind of what you would expect from heat capacity and specific heat. They're just off by a constant. And what you would expect is really that these heat capacities are going to be positive, because just in pretty much every system I could ever think of, if you're going to add energy to it, then you're going to increase the temperature, right? That just kind of makes sense. And so it's kind of a shock to me last year when I was taking a back-of-the-envelope physics class from Roger Blandford, who is, one of those amazingly famous astrophysicists. He said something that I thought was extremely strange, which is that if you're, forming a galaxy, as the particles radiate off electromagnetic radiation, they actually speed up. And that suddenly was really weird, because I was like, wait a minute, if you're losing energy because you're radiating, if you're radiating photons, you're losing energy, doesn't that mean the particles should slow down? And the answer is no. It turns out that these gravitational systems actually have negative specific heat. So let me give you a simple example, and then we'll generalize it. So let's pretend that, so I'm going to draw here, this is the sun. Oh, let me do this in a different color. So the sun is going to be orange, because that's the closest thing to yellow I have. And we usually represent it with a dot in the middle. And the Earth is going to be blue, because it's mostly water. And let's pretend for a second that the Earth is, we know it's actually an elliptical orbit. We can pretend that it's going in a circle. We'll say that the distance between these two guys is a capital R. And the question is, how fast does the Earth have to be going in order to maintain its circular orbit? So I'll write here in a circle, just to be absolutely clear. In a circle. Okay, so if you're moving in a circle, we can write out our force equations over here. force is equal to G m sun m earth over r squared. And to go in a circle, you have to set that equal to the centripetal force, which is m earth v squared over r. Solving this out, you're going to end up with v squared is equal to G m sun over r. Great, so if you're going in a circle, we can figure out how fast it's going all the way around. And if you know anything about circular orbits, you know that this velocity has to actually be the same at every point. And so even though gravity is accelerating you, all the acceleration is doing is changing the direction of your velocity vector, not the magnitude. So let's look at some other things. So the other thing that you know is that the force is equal to the negative gradient of the potential energy. And so if you're looking at this force, the only potential energy that'll work is U is equal to negative G m sun m earth divided by r. I think usually in high school physics you see this written as like negative d by dx, negative du by dx. Yeah, and so you can just replace the x with an r and you end up with the same thing. And then we can also calculate the kinetic energy. So the kinetic energy of the system is 1/2 m earth v squared. We're just pretending that the sun is static right now. And so the kinetic energy is also 1/2 times G m sun m earth divided by a single r. And so I just plugged in this guy over here. Okay, so there's an interesting thing here. Well, you see that U is actually equal to minus 2k. And this relation is actually more general. It doesn't just apply to this one body going around this one system in a circular orbit. This is actually a statement of something called the virial theorem. And I was in an astrophysics class this week, and Rob Simcoe, the lecturer, he said that the word virial actually comes from this guy named Clausius. Clausius of the infamous Clausius-Clapeyron equation, if you've taken some sort of phase transitions class. And apparently Clausius was just like this dude who was really important for thermodynamics, and he really liked inventing words, so he invented this thing called the virial, which, by the way, in case you were wondering, is equal to, if you've got a bunch of things, if you've got a bunch of particles in some sort of system, if you add up all of their momentum vectors dotted with their position vectors, this is like defined to be what he calls the virial. And using this quantity, you can show that if you're in kind of an equilibrium type system where things aren't like entering or leaving the system or something like that, then you actually get this exact virial theorem, this thing over here. Okay, so that's just kind of an aside because I thought that was cool. Clausius is important because not only was he kind of like a father of thermodynamics, he also coined the word entropy, which is probably what I'm going to be talking about next week, assuming I can get some of my reading done. But yeah, so that's the virial theorem, and it actually applies to general gravitationally bound systems, not just this simple system that we're considering over here. So that's the virial theorem, but maybe extending beyond that, it's interesting to look at the total energy, which is just the potential energy plus the kinetic energy. And if you plug in the virial theorem into this, you'll find that the total energy is actually equal to minus the kinetic energy. In the case of our simple system over here, this is equal to, I'll write this in purple to emphasize that it's for our system. It's negative 1/2 G m over r. So the m's are the two different m's. Okay, so let's think about this for a second. I told you that the heat capacity was equal to dE by dt. But we also know that in general the temperature of a system is equal to the average kinetic energy of the system. So in other words, the temperature measures how fast particles are moving on average. So if we plug this in, ignoring kind of the average sign, we'll see that this is negative dE or positive dE by dk. And if you take this expression over here and substitute it in, you'll find that this is equal to -1, which is less than 0. Sorry, and I have an incorrect statement over here. This isn't actually an equal sign. This should be like a tilde. The sign does not change when I consider dE by dt versus dE by dk. So we end up with dE by dt is less than 0. And so if you think about what that means, it means that as you take energy away, the temperature of the system is going to increase. What does that mean? So let's say I've got my sun over here, and I've got my earth over here, and let's say that all of a sudden, from my earth, I've sent off a lot of energy. Like, I shoot off a lot of energy. And so you would think that what this does is, because you're shooting off energy, there's less energy in the earth, and so it's going to slow down the earth, right? Because energy kind of measures how fast things are going, so if you lose some of it, then you're going to, go slower. But that turns out not to be the case for this gravitationally bound system. It turns out to be the case that because of the gravity, if your total energy, here, let me write this in red because it's really, really important. And red's awesome. So if your energy goes down, then your temperature, and therefore your kinetic energy, goes up. And this is totally weird. Because, it means that, when you're, if you have something, a bunch of charged particles circling, the sun or some other sort of, galaxy formation disk or something, these charged particles, as they are losing energy through electromagnetic radiation, so they're emitting photons, they're actually moving faster. They're getting pulled tighter and tighter into this gravitationally bound orbit. And so that's just totally freaking weird, right? There exists a system which we actually live in. We live on this, planetary system, where if you manage to decrease the total amount of energy in the system, everything would go faster. Yeah, and so that's, I think that's just totally weird, and it totally messes with a lot of my ideas of what thermodynamics were like. And it turns out that this is actually kind of maybe a tricky thing in general, which is that gravity, when we traditionally learn about thermodynamics and things like heat capacities and stuff, we only deal with really short-range interactions, short-range forces. And gravity, because it has this really long-range character to it, it really messes with our intuitive ideas of thermodynamics. And so hopefully next week what I'll talk about is actually kind of relate this to the expansion of the universe, starting from kind of talking about the thermodynamics of the universe, because the universe is kind of dominantly run by gravity, and so it causes all sorts of weird things. So for instance, the universe, we think that when it started, it was kind of a very smooth, homogeneous type of state. But so it's very smooth. Everything's kind of smoothed out, and you kind of think of that as like maximum disorder, maximum entropy. But if you look around today, we live in a very ordered world. There's lots of structure. There's things have collapsed into freaking galaxies and stars. That seems to be a lot more ordered than this really disordered initial state. And part of the reason that this just totally is weird, the part of the reason that this seems to violate the second law of thermodynamics. The entropy is always increasing, or the funny way to say it is, disorder is always increasing, but you started in an incredibly disordered state, and you end up in this, very ordered state with people walking around. yeah, so hopefully I'll get to talk about that next week. Otherwise, if not, it will be something else. But yeah, I just think this is kind of a neat system. It shows that there's a negative heat capacity inside of a gravitationally bound system. Yeah, that's it. Thanks so much.